I zapraszam do ostatniej części, czyli prezentacji laureatów ich wspaniałych i cudownych prac. Że teraz w zasadzie znowu podzielimy się na dwa streamy, na dwa strumienie. W tym strumieniu jako pierwszą prezentację będzie miała pani Julia Machnio z Akademii Górniczo-Hutniczej. Nie przewidujemy pytań. W tej części prezentacje są maksymalnie 10-minutowe. Gdyby chyba pytania mogą być, jeżeli sobie Państwo tego zażyczą, ale staramy się trzymać 10 minut. Także ja serdecznie gratuluję i oddaję głos pani Julii.
Dzień dobry, czy mnie słychać?
Tak, słychać bardzo dobrze. Teraz też widać.
I widać prezentację?
Tak.
Super. So I will present in English because there might be some non-Polish speaker here. So good evening, everyone. My name is Julia Machnio, and I would like to present my dissertation research, which is microstructural brain measures from diffusion MRI using deep learning. My supervisor was Mr. Tomasz Pięciak. First of all, we should start with a short introduction. The well-known process, the diffusion process, is a base for a diffusion MRI. In an environment that is not restricted, the molecules have a random motion, so the diffusion can be described as a Gaussian distribution. However, in an environment like human brain, this law cannot be preserved because the diffusion is always anisotropic. During the acquisition of the diffusion MRI data, the noise occurs, and as a result, the image quality is lower and lower, and the medically valuable information can also change. To remove the noise component from the images, we need to use some methods. For example, the techniques that are based on a deep learning algorithm. Most of the methods look quite promising. However, they need to use the reference data or the pseudo-reference data to work properly and to validate the algorithm. And one of the newly proposed technique is a deep DTI proposed by Canada in NeuroImage 2020. These techniques propose how to generate the pseudo-reference data, and this is by using the tensor, the diffusion tensor in each voxel. However, the problem with the tensor is that it assumes that diffusion in our brain has only Gaussian distribution, so everything that is non-Gaussian is cut off, and this is why, as main aim of my work, I propose to find a new technique for generating the pseudo-reference data and to improve the data denoising based of deep learning. Such techniques should allow to generate the pseudo-reference data automatically based on the in vivo data. It should also take into account both the Gaussian and non-Gaussian part, the diffusion in brain tissue, and most of all, it should not change the original signal. As a solution, we propose to model the signal with a spherical harmonic function represented in an orthogonal base. Here are the first results that we obtain. First column shows the original image, second the spherical harmonic image, and the last column the tensor image. As you can see, even on the pseudo-reference data, there are visible changes between the original image and the tensor image, what we cannot see that much in a spherical harmonic image. here, the results, the second results show the difference mapped between the original images and a modeled pseudo-ground truth. The cut-off noise, the cut-off part of the signal is in spherical harmonic image is mostly the noise, but on the tensor we can see that the cut-off part can be up to 20% of the signal. So the difference between the original image and the tensor is quite significant. What was also proved by the density histogram that is visible on the right side. As the actual denoising, we used a convolutional neural network with a quite basic architecture, and this architecture was optimized for each gradient strength. The results, the third result, show the differences between the original image and the spherical harmonics and the tensor, but after using of a convolutional neural network. So those images are actually denoised. We can see that the noise is much lower, but for spherical harmonic image, it is still quite close to the original image, but for the tensor, the difference gets higher and higher. But that was only the structural part of the diffusion, and we should also take into account the microstructural part. So this is why we also use the biophysical model NODI, and here is the orientation dispersion index. What is really important that in this biophysical model, we haven't seen any differences between the original data modeled for 90 direction and for the 50 direction, which is 6 times less than for our pseudo-ground truth. So we can assume that the method, the technique that we proposed based on the spherical harmonics does not change any microstructural information, even though that there was a small part of the signal that was cut off. It was mostly the noise, but still there was a small part of the signal that was not changing any microstructural information. So as a conclusion, the proposed techniques allows to generate the pseudo-reference data independently of the used gradient. It allows to denoise the diffusion MRI for a few times lower number of used direction without any visible changes. In comparison to the deep DTI method, it takes into account both the Gaussian and non-Gaussian diffusion, and the important part that it can be implemented in a clinical usage really easily, because it does not require any extra computational methods. So the method is simple and it can be easily used in a clinical usage. Thank you for your attention.
Thank you very much. Dziękuję bardzo za prezentację, doskonałą pracę. Oczywiście gratulacje jeszcze raz. Chciałbym przy okazji jeszcze tylko powiedzieć, bo my w niedługim czasie uruchomimy platformę prac dyplomowych. To jest do wszystkich Państwa, nie tylko dyplomowych, platformę tematów, projektów. Pewnie większość z Państwa będzie planowało pójść jeszcze na studia magisterskie, albo już Państwo są na studiach magisterskich. I dzisiaj mieliśmy spotkanie z dziekanami i z firmami, gdzie firmy będą mogły wprowadzać tematy do realizacji na uczelniach, więc myślę, że coś takiego byłoby dla Państwa też ciekawe. Proszę nas śledzić, może też polubić na LinkedInie, właśnie dodałem link. Także zachęcam też do dłuższego obserwowania, bo będzie się pojawiało więcej produktów. Dziękuję Pani Julii.